Did anybody not put their name on this weird piece of paper that I handed out on Monday? Anyone? It's just a seating chart, so you just put where you sit. Thank you. It's helping me figure out your names. Is Ethan here? I have an old quiz for Ethan. Thank you. Adam. Okay, great. So mini quiz, as you know, phones away, computers away, funny rings, don't look at them, or funny watches, and you can talk with anybody you like. For one of the CAs, if they're here later. Go ahead and pass this back. You can draw on the board, you can talk to your neighbors, you can talk to the next table. As long as you're talking out loud, you're doing it right.
Not necessarily true.
Oh, a little extras in the back. Needs one, right? Thanks. I know this one takes a little bit of time to read, but once you read it, you should be talking out loud with your desk. Yeah, I don't know. Just you and you're talking. Thank you for asking.
No, it's a
I think there's some extras in the back of this quiz if you can find them. Feel free to ask the people next to you at the different table if you want to check your answer.
Well, the thing I'm not like, what is the difference between the global focus out?
IROF is the derivative rate. You find the rate of change of the point and then average rate of change.
Raise your hand if you want 1 more minute. Anyone? All right, I see a few. I'll give you the minute. Get your answers down. All right, hand them up.
I like that.
Thank you. Is this all of them? No more? All right, what do you think the answer is? Raise your hand if you think the answer is A. Raise your hand if you think the answer is B. Raise your hand if you think the answer is C. Raise your hand if you think the answer is D. All right, so we have like a third A, a third, I think it was D, and a third did not raise their hand. Okay. So let's take a look. So we have a function. It's continuous and differentiable everywhere from 3 to 5. So it's super nice from 3 to 5. I'm drawing a little tiny picture over here. Okay. It also has the property that f of x is equal to 2 at both of those places. So in a way, those are like my thumbtacks because the function is continuous on the closed interval. It's going to start at one of these points, right at that point, move around somehow to get to the other point. And the fact that it's differentiable on the interior means it's not going to do that in a pointy way. It's going to do that in a smooth, continuous, curvy way the whole way. Okay. So that's all we know. Now, there could be a lot of ways the function looks in between. It could look like this. It could look like this. It could look like that, right? We don't know. All we know is it's connected in some smooth, curvy way, but we can still guarantee that certain things happen. So for example, let's start with D. We want to know which is not necessarily true. The average rate of change on 3 to 5 is the slope of this line right here. That's how much the function changed on average from 3 to 5 because it started out at the same height. So on average, it changed 0. So, or you could just compute it. If I wanted to compute that average rate of change, I would do f of 5 minus f of 3 over 5 minus 3. That's just the formula for average rate of change. And that'd be 2 minus 2 over 2, funnily enough, which is 0 over 2, which is 0. So we do get 0. So this is actually true, this one here. So D is true, is not the answer to this quiz because it's true. Which is another one you think is probably true? B. There's some C in the middle for which F has a horizontal tangent line. You know what? That's actually here, like here there's one, here there's one, no matter which function it looks like, there's somewhere in the middle that the function has to have a horizontal tangent line because it has to turn around at some point. And at that point, it would have a horizontal tangent line. It can't have a point because it's differentiable. It has to have a horizontal tangent line. What is the name of the theorem that guarantees that? We learned 2 theorems last time. You could actually say either one and it would be technically right. So say one of them. Rolle's theorem. So Rolle's theorem said that technically we needed the 2 values to be 0, but it's actually true even if the values are anything. So this is kind of like a slightly stronger version of Rolle's theorem, but it's also the mean value theorem. The mean value theorem says there's a place in between where the average rate of change, which is 0, is equal to the instantaneous rate of change. There's somewhere where that happens. There's somewhere where the average rate of change, which is 0, is equal to the instantaneous rate of change. And that would mean there's somewhere where the derivative is 0. In fact, that's what C says. There's somewhere the derivative is 0, somewhere it has a horizontal tangent line. Those are actually the same. So B and C are actually saying exactly the same thing, and they are both true. The one that is false is A. Why is A false? Go ahead. Well, let me rephrase what you're right, that it's because of this x minus 4. But let me rephrase a little bit because it actually could happen, right? This very first picture I drew here, the highest point was in the middle, maybe at 4. So it could happen that there's a horizontal tangent line or instantaneous rate of change right in the middle, right? But it doesn't have to be right in the middle. It could be anywhere, right? So there's all kinds of ways the function could look in between. It just can't be broken. It can't have a jump. It can't have an asymptote. It can't have a point or a cusp in it. It just has to be nice. But we don't actually know where it goes and how it goes there. It could be in the middle that it turns around, but maybe not.
So that way it's not necessarily true.
That's why it's false. We can't guarantee that that's true. That statement is not necessarily true. It could be true, right? But remember, a statement is true if it's true all the time, and it's false if it's false even one time. And in fact, this thing is false way more often than it's true. So it could be true, but it's not necessarily true. Notice how the logic section from chapter 0 is coming in here too. There's a lot of if-then type statements or implication type statements. Actually, not that many here, but the concept of what is true or false is. Okay, so that's how this one worked. Are there any questions about this? This type of abstract problem is going to keep happening because we don't want to just compute derivatives. Or, I mean, we like to compute derivatives, but you know, a computer can do that, right? We're here to interpret things that we can conclude from information we're given. Okay, so this kind of non-calculational question is likely to occur many times. Okay, let's see. How do I put this back? Thank you for answering the sports question. It gets you to open poll everywhere in case you have a question. I'd like to know that you can ask it. I'll leave this open, and it's kind of inactive recently, so someone may have to point me to it if there's a question on it. Okay, so last time we did all this abstract stuff. We did the mean value, Rolle's theorem, the mean value theorem. Today, much more practical. Okay. First of all, we already know from way back in chapter 0 that the slope of a function, like whether the function is increasing or decreasing, we can see it right on the graph. And now we have a way to measure when a function is increasing. It's not just when the function is going up, like we saw in chapter 0. Every point on the graph here where the function is going up as we go left to right, every point has a tangent line with a positive slope. And when the function is going down, every tangent line of the function has a negative slope. And when the function is going up, every tangent line again has a positive slope. So if we draw f prime, here's a picture of f prime. The heights of f prime are the slopes of f. So in these tan regions, the slopes are positive, so we draw them as positive heights on the graph of f prime. And in the middle part, the slopes are negative because the function's decreasing, so we draw the derivative as negative. This is a good time to abolish the word it, okay? If I say, because it is increasing, it is positive, that is confusing because there's two its here, right? There's the original function and there's the derivative. So we don't ever want to say it, we want to say the function or the derivative, depending on what we're referring to. So I say when the function is decreasing, then the derivative is negative. That's very important because you can't just like conflate decreasing and negative in your head. Those are two different things. And you know, sometimes your gut instinct for like what words go together in an English kind of way don't work. And you also need to know which one is the function and which one is the derivative. So when the function is increasing, the derivative is positive. When the function is decreasing, the derivative is negative. So that's pretty cool. Because if you think about it, in chapter 0, we spent a lot of time learning how to tell when some function is positive or negative. So we can apply those techniques to tell when the derivative is positive or negative, and that will tell us when the function is increasing or decreasing. Like for example, oh, I'm not ready to do that yet. All right, we're going to do a little matching exercise first, and then we'll do what I was about to do. I made you a worksheet. It's very tiny up here. It's hard to see, but it should be a little bit better on the worksheet itself. I don't know why I can't manipulate paper today. Here you go. Another one, the big one today. Go through that, ask me questions about it. I'm also going to open up one of those things where I can move things around. But let me tell you what's going to happen. In this box, these are all functions, and these are all derivatives, and you have to match the functions to the derivatives. And this is a harder group, right? These are all functions, these are all derivatives, and you have to match the derivatives to the things that are derivatives of, okay? So in each box, the first box is easy ones, functions and derivatives. Second box is harder ones, functions and derivatives. And I'm going to see if you're bringing me some extras. Thank you. You don't have to do that. I can always come back and get them. I don't want to take your time. Okay. Okay, so remember, just start with the first box. Functions on the left, match the derivatives on the right. Can we just do one that's easy to make sure we get started? Like, can anyone tell me that for this graph right here, up here at the top, that's a function. What should its derivative look like? The bottom one, it should be constant slope all the time, and it's a positive slope. So, oops. So you can't do this, but I can. I'm actually just going to move it over here. And I'll move that one out of the way. I'm going to move these over. Okay, so this is the function, and I've moved the derivative up here. Of course, you can't move it. You'll just connect them with a line. Maybe it's better if I connect them with a line so that it will look like your page. So let me see if I can figure out how to do that. There we go. Is that better? Because now it looks like your paper. The first one up there, its derivative is the bottom one. Try to pick off the easy ones first. Anyone want to suggest another one? The second function is the first derivative, right? This one has a constant negative slope. And that's a picture of constant negative slope up there. So the derivative of this graph is this graph. We're just using the fact that when the function is increasing, the derivative is positive. When the function is decreasing, the function is negative. When the function is constant, the derivative has a constant slope, the derivative is constant. What's up with this one? With the absolute value, what's going to happen right there? Yeah, it's going to be a jump. Because everyone, what's the slope like here on this map? Positive or negative? Negative and constant, the same number all the time. And then over here, the slope is positive and the same number all the time. And in the middle, it has to jump. It's this picture right here, the second to last picture. I'll connect that too. And then I'll let you figure out the last three without me interrupting. One place to start is looking at where the derivative is zero, just so you know. Here the derivative is 0 at -1. So the derivative function should have a root at -1. For this one, the derivative has 2 zeros. So the function should have 2 zeros. And here the function has a derivative of 0 at 0. So the derivative should have a root at 0. That should actually tell you the rest of this entire set. In fact, let me do that so I can get to the next ones. This one here, the fourth one that I just put yellow on, it has a derivative of 0 at -1, and the only function here that does that is that one. So horizontal tangent line here means a slope of 0, which means these two are connected. Notice that here the slopes are negative and then they're positive, and that's exactly what happens here. The heights of the derivative are negative and then the heights are positive. I'm going to do the last two and then I'm going to move away from here and walk around while you do the second box. So this one here has 2 roots of the derivative. It's going to be this one. Notice here the derivative is 0 at these 2 places, and there's a horizontal tangent line. I didn't do that very well, but at these 2 places. And then of course that tells you what the last one has to be. This one has to connect to that one. You might remember I said once that things that are like cubic turn into quadratics when you take the derivative, right? The power goes down by 1 If it's a power function, then quadratic functions have derivatives that are linear. Cubic functions have derivatives that are quadratic. 4-degree functions have derivatives that are cubic if they're polynomials. Yeah.
So if you have the constant
If I had a f that was that,
like just the
Yeah.
horizontal line.
I would say if you had a horizontal line, no matter how high it was, the derivative is constantly 0. So the derivative is the function that's 0 all the time. Because like unlike this one, where the slope was positive, so we had a slope of 2 all the time, I would just have a slope of 0 all the time. It would be on the x-axis. Yeah. Okay, so that's a tangled mess of lines, but hopefully the colors will help you figure that out. Now do the second box. This one's going to be hard even for people that have had calculus before. You're going to have to think about the asymptotes, kind of like something we did at the beginning of chapter 2, actually. And you want to try to connect each function to their derivative. And if you get some, you can ask me to check them out, and I'll tell you whether I. If you have one and you want to check it out with me, just ask me. I'll tell you whether I agree. Yes. Oh, all of it. Well, which ones are you not sure about? So this one, where does this connect to? Here. Oh, I agree, because that's not even defined over there. And this one's not even defined over there, so it kind of has to be that one. Also, this one is a positive slope all the time. When the slope starts up high and gets lower. And this is positive all the time, starts up high. Oh, I agree with this one.
It goes to 0.
So you're going to make that same type of argument for any of them. If there's one that doesn't make sense, you call me back. Yeah. Yeah, I agree here. The slope seems to be vertical, which wouldn't affect infinity. So it should go, yeah, I think it's happening. And the slopes are becoming 0. And
Well, because it's like.
And also here the slopes are positive. And then there's like
Stop right before 2. The other one is like.
oh, and then they're positive again. And these heights are positive. And then the heights are positive. I would have to think more. Yes, yes, yes. Yeah. Which one? No, it's in the bottom. I think they're out there. Which one you want to know? This one here? And you have to do this one? Well, it definitely agree that the funds are not defined as 0 and this one's not defined as 0. I agree that the slopes are approaching 0 at the end, and these heights are approaching 0. This one, that's good. I can see the slopes are all negative here, and then they are negative again. Right? They're negative both times, and these heights are negative both times. Yeah, in fact, also the slopes are shallow negative, and then very steep negative, and these heights are small negative and large. So, yeah. Yeah. Yeah, the slope maybe is even a vertical line here, amplifying, and so you have slope is flattening out to 0, height is going down to 0. Slopes are positive on both sides of the weird point, height is positive on both sides of the weird point. So yeah. Yes. 3 so far. 3. All right. Well, let's start with this one. This one, the slope should be like 0 at the end, so you keep coming back in. But the slope should also be 0 in the middle. And you have the slope being not even defined. But Yeah.
Did it all, not all.
Slope of 0, 0, there's a 0 there. The slopes are positive going up to this point, and take the positive. And slopes are negative after that point. The heights are negative. Yeah. Try it for the others and then tell me back. You look like you have a question, but I can't tell. Okay, is there one you're not sure about? Well, how about you know what they are? And you guys can figure it out. Let's start with that. You guys want to see the answers?
Yes.
Yeah? All right. Now, this is a little weird because instead of drawing lines, I actually organized them next to it. So each one of these pictures is the function and then its derivative, which is not in the same height anymore. Okay. But this is what we get at the end. Notice for this first one, the function is not even defined on the left-hand side. That's a huge giveaway because if the function is not defined there, there's no slopes and the slopes aren't defined there either. That's a huge giveaway. Notice that every time the function flattens out at the ends, like here and here, the derivative heights go to 0 because the slopes are going to 0. I'll let you take a minute to figure out how to connect your lines based on what I've shown you here, because I know that's a pattern matching exercise, and then you can ask me about specific ones. Yes.
So the first one,
Yeah,
the derivative is like the complete opposite.
it is kind of,
Does that work?
but it's because here the slopes are positive. The slopes are very high, and then they become lower. And that's a description of the heights over here.
Oh.
The heights are very positive and high. They stay positive, but they get lower and go to 0. You got to remember that everything in the first column that you can say about slopes is what you should say about heights in the next column. That's a weird translation to make, but that's the relationship. Okay, let's do something a little bit more calculation. Oftentimes, instead of wanting to know where a function is increasing and decreasing, which we could do with a number line, I just want to point out that like here, this function, if the function is increasing and then decreasing, that means that the derivative here in red is positive and then negative. So we could do this with a number line. We're going to do it in a minute. But in addition, you can tell when a function is having a max or a min from this type of information. This is the type of information you can compute by taking the derivative, setting it to 0, making a number line. If you see a number line for the derivative that says the derivative goes from positive to negative, that means the function was increasing and then decreasing. And if it's continuous and differentiable, then right in the middle there, it's having a max. And the same thing here, if the function is decreasing and then increasing and everything's continuous and differentiable, sorry, if the derivative is negative and then positive, then the function is decreasing and then increasing, and the function must have a minimum in between, like this. Sometimes you see plus plus or minus minus. Those are the cases where you have a critical point, but it's not an extremum. Okay, so these are the 4 possible cases. These pictures are in your book. So you don't have to worry about copying them all down. They're also here in the slides, but let's see how to use this practically, okay? With an actual example, like a classic calculus problem. Here is a function. It's a cubic. I know it's doing this kind of thing, right? Like up, down, up. I could try to find the roots of this cubic. That actually is kind of difficult for this cubic. I don't know how to factor it. It doesn't factor easily. And then the problem is actually asking me something even harder. Where is the function going up or down? And where are the extrema? And again, we know the function looks probably like this. And we're asking like, you know, here's where it's increasing. Here's where it's decreasing. Here's where it's increasing. Here's a max. Here's a min. So we have some intuition about it. But like, what are these values? Is this happening at x equals 2? Is it happening at x equals 10? Is it decreasing from like -5 to 5 or from 0 to 11? Like, I don't know, right? That's what I want to find out. So I have some intuition for what the picture must look like, but I still don't know the actual values. And that's what I'm going to do with calculus, okay? And in fact, you don't even need to have this intuition to do the calculus problem. You can just do the calculus problem. I want to point out that you do actually know something at the beginning. So what happens first? Okay, so first of all, I'm going to take the derivative and factor it. The reason I want to factor it is I'm curious where the derivative is 0 because I want to make a number line. So this derivative is very easy. Power comes down, we get 2 times 3x squared, that's 6x squared, minus another 6x squared, 6x, no, this is 6x, not 6x squared, 6x. The derivative of 3 is 0. So this is the derivative right here, 6x squared minus 6x. And then if I want to, I can factor out a 6x. Yeah.
So just clarifying,
Yeah.
that's just the number without, like,
0. That's right. That's right. But again, banishing the word it, when the function is just a number, or a piece of the function is just a number, the derivative of that part is 0. Yeah. It's hard to get rid of the word it, right? But starting, and then next week, we're going to have 3 its. We're going to have the function, the derivative, and the second derivative. So I'm not kidding around about the it. Like, don't say it anymore. Okay. It's hard. So, okay, I take the derivative, I factored it. And why don't you try? Oh, I have a handout for you so you have something to write on in case you didn't bring it. I'd like you to try on your own to make a number line for the derivative. Just like we used to do in chapter 0. We would make a number line where we would mark tick marks where the function we were interested in, which in this case is the derivative, we would make tick marks where the function we are interested in is 0 or does not exist. So you're going to put tick marks where this derivative is 0 or does not exist. And then we would test a point in between each of those tick marks to see whether the thing we were analyzing was positive or negative. Tell me again, what's the thing we're analyzing? The positive and negative of the derivative, not of the function. The question didn't ask us that. The question asked us increasing, decreasing of the function, which is positive, negative of the derivative. So what you're doing now is making a number line for the derivative with pluses and minuses on it. But you're going to get it from here. This is 0 when x is 1. And this part's 0 when x is 0. So the 2 tick marks on your number line should be 0 and 1. That's my hint to everybody. The tick marks on your number line should be 0 and 1. And then you got to put pluses and minuses in between the 0 and the 1 and on the outside. All right, do you want another minute? Anyone? Or do you want to see the answer? Answer. Okay, so here's the number line. Like I said, the derivative, that's the thing we're interested in analyzing. It's 0 when x is 0 or when x is 1. There's no place where the derivative doesn't exist. So there's only 2 places to mark on my number line. And look at this new thing I've added to the number line. That's to remind me, this is not a number line for f. I'm not answering when f is positive or negative. I'm answering when f prime is positive or negative. Okay. And then you test some points, like when f prime of -1, if I plug in -1 here, I get negative times negative. See that here? Negative, negative. That's positive. If I look in the middle at like a half, I plug it into the thing that I am analyzing, which is f prime. If I plug in a half, I get positive and negative, plus minus, that's negative. And then finally, you know, I like to plug in a big number sometimes just because I can. To do the whole other side, I can just plug in 100. This is clearly positive, positive. So this interval is positive for the derivative. So I would like you to now answer, see if you can answer which intervals is the function, not f prime, but f, increasing. Which intervals is the function decreasing? Is there any max and where is it? Is there any min and where is it? See if you can answer that just from this number line. Behavior of f from the information about f prime. Let me give you a hint. This plus, this first plus here between minus infinity and 0. What is it that's positive? The derivative, that is the slope. So the function is doing what? Going up. So you can actually make a little increasing symbol here for f. Make like sort of a row of what happens to the function. Would you like to see? Who would like to see now? Who wants another minute? Nobody. Okay, here we go. So like I said, this row here is an interpretation for f. Look, I labeled that f. So the plus minus information about f prime tells us going up and going down or increasing, decreasing information about f. Where the derivative is positive, the function is increasing. Where the derivative is negative, the function is decreasing. Where the derivative is positive, the function is increasing. In between, if the function goes up and goes down and it's defined in continuous differentiable here, that's got to be a max. And if it goes down and then up and everything is continuous differentiable and nice and defined there, then that's got to be a min. It's exactly this shape, right? The function goes up, goes down, goes up, just like we thought. And now we know that this is happening at 0. So I could actually, why do I only have green? Well, I have green and blue. Actually, know now that the maximum is at 0 and the minimum is at 1. That's what I know. I actually don't know how high or low this function is. You know, the x-axis could be up here or it could be way down here. I don't actually know from the information in the problem, but yet I could figure it out if I wanted to. In fact, if I plug in 0 for x, I get 3. So in fact, this height right here is 3. And oh, if I plug in 1 for x, I get 2 minus 3 plus 3. So this is 2 right here. If I really wanted to, I could plug stuff in and figure out how high those maxes and mins are if I really wanted to. So this is what the picture looks like. I don't need this where anymore. Nowhere. And notice here, I'm reading right off the number line. This is exactly what we used to do in chapter 0. But instead of saying where f is increasing, we would have said, oh, this thing we're analyzing is positive on this union of intervals. And the thing we're analyzing is negative on the middle interval. But now the conclusion is that that means that f is increasing on the union of the two on the outside. F is decreasing in the middle. And notice I've said where the maxes and mins are by where their x values are. I can tell you how high they are, their values, if I want to, but their locations are at 0 and 1. So when you do this thing with the max and the min, that's called the first derivative test. Let me just go back to this slide for a second. We had this situation, plus minus, followed by this situation, minus plus. The first derivative test says every tick mark you have, you can analyze it to see if it's a max, a min, or a neither. Remember, every tick mark is where the derivative is 0 or does not exist. What's the name for those points? The critical points, right? Critical points of the function are where f prime is 0 or doesn't exist. So really, you're testing those critical points and any weird points on the function. Okay, please hold on to that paper because the next problem we're going to do is this one. We're going to do it on Friday. So feel free to do it in advance if you like, but just put the paper into your notebook so you'll have it again on Friday because we're going to start with that on Friday. Have a good day, everybody.